Waves are everywhere. We encounter waves on a daily basis. Sound waves, waves on a string, and slinky waves are just a few of the examples of our daily encounter with waves. For many people, the first thought concerning waves conjures up a picture of a wave moving across the surface of a lake, pond, or other body of water. The waves are created by some form of disturbance, such as a rock thrown into the water. Another perfect example of disturbance is a long rope tied to one end. The up and down vibration of the end of the rope created a disturbance of the rope that then moved towards the other end. Upon reaching the opposite end, the disturbance often bounced back to return to the end where it was being held. A single disturbance could be created by a single vibration of one end of the rope. On the other hand, a repeated disturbance would result in a repeated and regular vibration of a rope. A wave is a disturbance which travels from one place to another, carrying energy without carrying any material. Many waves have a characteristic speed. The size and shape of the wave does not affect how fast it travels. The amplitude of the wave is the maximum height relative to the normal. Harmonic waves, or sine waves, form a regular repeating pattern. The frequency of a harmonic wave corresponds to how many times each second through a particular spot it goes through its repeating cycle of motion. The corresponding wavelength is the distance over which the pattern repeats. The distance for the repeating pattern in space at the time for each cycle are related to each other through the wave velocity. The time it takes one wavelength of the wave to pass a given point is the same as the time it takes that one point to go through one full cycle of its motion. Thus, for each harmonic wave, the product of a wavelength and the wave frequency must be equal to the wave velocity. So a wave with longer wavelength will have a lower frequency. Shorter wavelengths have higher frequencies. Waves come in many shapes and forms. While all waves share some basic characteristics, properties, and behaviors, some waves can be distinguished from others based on some observable characteristics. One way to categorize waves is on the basis of the direction of the movement of the individual particles of the medium relative to the direction that the waves travel. Categorizing waves on this basis leads to two notable categories: transverse waves and longitudinal waves. A transverse wave is a wave in which particles of the medium move in a direction perpendicular to the direction that the wave moves. Suppose that a slinky is stretched out in a horizontal direction, and that a pulse is introduced into the slinky on the left end by vibrating the first coil up and down. Energy will begin to be transported through the slinky from left to right. As the energy is transported from left to right, the individual coil of the medium will be displaced upwards and downwards. In this case, the particles of the medium move perpendicular to the direction that the pulse moves. A longitudinal wave is a wave in which particles of the medium move in a direction parallel to the direction that the wave moves. As a pulse is introduced into the slinky on the left end, energy will begin to be transported through the slinky from left to right. As the energy is transported from left to right, the individual coils of the medium will be displaced leftwards and rightwards. In this case, the particles of the medium move parallel to the direction that the pulse moves.